Hello, my name is Mildred. In this lesson, we will learn about correlation analysis.
What is correlation analysis? Correlation analysis is a statistical technique used in exploratory data analysis to measure the strength and direction of the relationship between two numerical variables. It helps answer the question, when one variable changes, does another variable change as well? Correlation does not prove causation, it only measures association.
Why correlation analysis is important in exploratory data analysis? Correlation analysis helps us identify relationships between variables, detect potential predictors for modeling, reduce redundant features, understand patterns before building models, generate hypotheses. It is typically performed after summary statistics and distribution analysis. The most common correlation measure is Pearson's correlation coefficient, R.
Types of correlation. Positive correlation means that as one variable increases, the other increases. On a scatter plot, this will show an upward slope. Negative correlation means that as one variable increases, the other decreases. On a scatter plot, this will show a downward slope. No correlation means that there is no predictable relationship. On a scatter plot, the points appear scattered randomly.
Strength of correlation. 0.00 to 0.19 means very weak. 0.20 to 0.39 means weak. 0.40 to 0.59 means moderate. 0.60 to 0.79 means strong. 0.80 to 1.00 means very strong.
Types of correlation measures in exploratory data analysis. 1. Pearson correlation. Pearson correlation measures linear relationships. It assumes normally distributed data. 2. Spearman rank correlation. Spearman rank correlation measures monotonic relationships. It works for nonlinear patterns and good for ordinal data. 3. Kendall's tau is an alternative rank-based method. It is robust for small datasets.
Limitations of correlation analysis. It only measures linear relationships. It is sensitive to outliers. It does not imply causality. It can miss nonlinear relationships.
When to use correlation in EDA? Use correlation analysis when variables are numerical. You want to explore relationships. You are selecting features for modeling. You want to detect multicollinearity. Next, let's generate the correlation matrix of our dataset.
On the screen is a code snippet that shows how to generate the dataset's pairwise correlations between numerical variables. We see the output when we run the code.
What did this output mean? What the diagonal means? Notice, age with age is 1.0. Study hours with study hours is 1.0. Attendance with attendance is 1.0. Exam score with exam score is 1.0. This is normal. Every variable has a perfect correlation with itself. How to read the other values? Correlation values range from +1, perfect positive relationship. 0, no linear relationship. 1, perfect negative relationship. Now let's interpret the actual relationships.
Interpretation of each relationship. Age and study hours has a value of -0.113670, which means very weak negative correlation. Meaning that as age increases, study hours slightly decrease. But the relationship is extremely weak. Practically, there is no meaningful connection. Age and attendance has a value of 0.073022. This means it has a very weak positive correlation. Meaning, older students attend slightly more, but the value is close to 0, which then means that there is no meaningful relationship. Age and exam score has a value of -0.019837, which means an almost zero correlation. Meaning, age does not influence exam performance. Study hours and attendance has a value -0.088228. Very weak negative relationship. Meaning, students who study more do not necessarily attend more. There is no meaningful connection. Study hours and exam score has a value of minus 0.013846, almost zero. This is interesting. It means, in this dataset, study hours are not related to exam scores. Why? Because the data was randomly generated. There is no built-in dependency between these variables. Attendance and exam score has a value of minus 0.031535. Again, almost zero. Meaning, attendance does not predict exam performance in this data set.
Overall conclusion. Every off-diagonal value is very close to zero. That means, there are no meaningful linear relationships between the variables. This is expected because the dataset was generated randomly without a formula linking variables. This result demonstrates, correlation analysis helps confirm whether relationships exist. Even if we expect study hours to affect exam scores, the data does not support that here. Data must drive conclusions, not assumptions. What this means for modeling. Since correlations are near zero, linear regression will likely perform poorly. Variables are not predictive of each other. No multicollinearity issues exist. This is good news. Let's now visualize the heat map. On the screen are code snippets to visualize the heat map and the resulting heat map. This allows quick identification of strong relationships.
In the next lesson, we will discuss crosstabs and pivot tables. If you enjoyed this lesson, give us a like, subscribe to the channel, or leave a comment. We appreciate your support. Hope to see you in the next lesson.